So I'm going to do exercise 1.6 from Atiyah and Macdonald's Introduction to Commutative Algebra. So the exercise is as follows. Let A be a ring such that every ideal not contained in the nil radical contains an idempotent E that is non-zero. So what this means is that if we have an ideal that's not contained within a nil radical, we have an element E such that squared gives the element back, and the element is not 0. And it's obviously not 1 either, since 1 is a unit. And we have to show that the nil radical of this ring equals the Jacobson radical of this ring. So let N denote the nil radical and let R denote the Jacobson radical. So when we want to show that two sets are equal, we just have to show inclusion on both sides. So we have to show that N includes R and R includes N. We already have one of those for free actually. We know that the nil radical is contained within the Jacobson radical. Well, why is that? Because the nil radical is the intersection of all prime ideals. And the Jacobson radical is the intersection of all maximal ideals. So what this means is that if we have an element that's contained within every prime ideal, it has to be contained within every maximal ideal because every maximal ideal is prime. Good, so we know that the nil radical is contained within the Jacobson radical. So we have this side. Now we have to show that the Jacobson radical is contained within the nil radical. So how we're going to show this is by a proof of contradiction. And we're going to assume that we have an element from the Jacobson radical that is not contained within the nil radical. Right? What we can notice that the ideal generated by it is not contained within the nil radical. So by the exercise, this ideal contains an idempotent. And that in particular means that we have a ring element from A such that R times that element is equal to the idempotent. Good. So now we can make use of a fact of the Jacobson radical. Namely, we know that 1 minus Rx, right, for any element R in the Jacobson radical, for every element from A, is a unit. So again, if we have an element from the Jacobson radical, then 1 minus Rx is a unit for all x in A. So what this means in particular is that 1 minus this idempotent is a unit, because we can just say, okay, Ry, 1 minus Ry is thereby also a unit. So 1 minus E is a unit. Okay, but once we have that, we can say, okay, so let U be this unit, right? And we're just gonna perform some basic algebra. Namely, we're gonna distribute this unit over the brackets. We're gonna get U minus EU is equal to 1. We're gonna multiply by the idempotent, and we can easily see that, well, we've used the identity of the idempotent here. So we get 0 equals the idempotent, which is clearly a contradiction. And so we've shown that elements that are in the Jacobson radical also have to be contained within the nil radical.